All right, everyone. Hello. Welcome. Good evening. So today, we're going to do a quick finish up circular motion. We'll get into Newton's laws. But before I do that, because two-dimensional motion is so tricky, because two-dimensional motion is so many pieces that you have to remember, I've gone ahead and given you all an extension on when the quiz is due to Tuesday at midnight. So just a few extra days. May matter to some of you, may not matter to others, whatever. So your quiz for 2D kinematics will not be due until this Tuesday at midnight, so instead of Saturday. If you have already done both your attempts and it's gone great, fantastic. If it has not gone great and you've done both your attempts, shoot me an email. We'll figure something out to make certain everyone has kind of equal opportunities. But if you've done one attempt, then you just got a lot of time to kind of polish things up. So that's I'm not too worried about that. But yeah, if you've done both attempts and they haven't gone well, shoot me an email. We'll figure something out. Since you obviously didn't know I had that extra time. This is for 2D projectile motion, 2D kinematics, which was due this Saturday. Okay? All right. What I also want to mention is just some reminders for 2D kinematics, because 2D kinematics has a lot of, I don't know if nuance is the right word, but it has a lot of things that you just kind of have to know that aren't on the formula sheet. Now, they are things you can add to your 5x8 note card. I think I may have misspoke last class and said 3x5. Remember on your all's test, you get a 5x8 note card. It's about yay big, 5 inches by 8 inches. You can write in the front and back. It's a good amount of space, basically, for anything you would need. You can't fit the solutions to every single, I mean, you can try. But I don't think you can. So, anywho, 5x8 note card is the one you'll have access to. And you can put some of these things on there. So one of those things is that the time to the top is the same as the time back down if it returns to the same height. That is only true if it returns back to its initial height. If instead this thing is going higher up or farther down, that does not work. So demo duck here, he's a great tool. So yeah, if the duck returns back to my hand, the time to the top is the same as the time to the bottom. If I catch the duck at a higher spot, the time back down is shorter. If I catch the duck at a lower spot, the time is bigger than that. So, reminder to you all, number 10, I think, number 10. The one where I'm launching something off a cliff at an angle, fantastic problem. Highly recommend you all solve, always solve all the practice, solve all the ones that are on your all's problem sets, because I put them there for a reason. If you can solve them all, awesome, you're good to go. If you can't, that's a flag that something's off and you should determine what's off. I am just attempting to get my thing actually charging. We'll see. Hopefully my laptop doesn't die. So there's that. Remember, X and Y are separate. Remember that hey, there we go. All right, let's kind of jump back to 2D kinematics, and I'll point out some things looking at the equation. Actually, let's pull out our equation sheet. Where are you at, equation sheet? Your test is made. There it is. I'm obviously not going to open it because it has all the answers highlighted. So I've made your all's test. Again, I got to double check that everything's kosher and the time is good on it. But it's made, hence why I was able to send out that announcement with what the details are of it. So, oh yeah, this is very sad. My pen battery is dying, so I have the pleasure of drawing things grossly. If you all use this equation to find the final velocity, it works great. No problem. Just remember, when you square root the right side, the answer can be plus or minus that. So easy example. Oh, I hate this. I'm going to type. Nah, I can't type. All right. Behold my finger painting skills. If VF squared equals, you do the right side, and you get 144, there is two possible solutions to that. One of those, so you're going to square root it. It can either be VF can either be plus or minus 12. How do you know which one it is? If it's falling, it's negative. If it's going up, it's positive. So when you all use this equation in a projectile motion problem, and say the cliff problem, if you want to find, hey, I launched something at an angle off the cliff, and you want to figure out the final velocity at the bottom when it hits the ground, if you know how high up the cliff is, that's your initial height. That's x, y naught. Your final height, that's at the ground. That's 0. Your acceleration is negative 9.8. Your initial velocity in the y direction is whatever you found. At the end, when it hits the ground, if you just square root this, your calculator is going to tell you positive 12. But that would mean that when it hits the ground, it's going upwards. And that doesn't make sense. It's negative 12. Very, very, very important thing that the math, this is where, again, the math is fantastic and all, but there's like, when it comes to physics, you have to think about, does your answer make sense, and realize positives, negatives, and all that kind of jazz. There's little things like this that you got to keep track of. When I take the square root, the answer can be plus or minus. Is it going down or is it going up? When it hits the ground, it's going down. So it's negative, okay? So please spend the time on these 2D kinematics problems. Send me questions. Because I've extended it to Tuesday, that means I will answer emails on Monday about any final questions you may have, Monday/Tuesday. Obviously, I can answer questions Tuesday as well. But just, note that I will answer those questions Monday, Tuesday, whatever, but just make sure you give yourself enough time as well. So that's part of the reason why I extended it. Okay. So, projectile motions, 2D stuff. Spend the time on it. It is taking basically everything we learned. It's taking vector stuff. We're seeing vector stuff. It's taking 1D kinematics. 2D kinematics is the culmination of all that. If you can do 2D kinematics, you can do 1D kinematics. It's kind of how that boils down. So that's why I'm giving you all the extra time on that. We are now kind of going into new stuff. So we talked about circular motion. The reason so I brought my duck. Here he is. So demo duck here, fantastic, love him. Demo duck is demonstration duck. He's been through some stuff. Anytime my high school class I need to demonstrate projectile motion, he gets chucked across the room. I throw him, but then I'd have to go get him. He'll get chucked in a second. So, to demonstrate this, I told you all last class that if something is spinning, the velocity, the direction of this tangential velocity, you just draw a little line, and then you make it bigger, and you make that line straight. That is the direction that it will go if it was released. So, demo duck here, online students, you can't see this, so you're just gonna have to, in your mind's eye. All right, so if this is clock, I gotta orient myself. Gosh. All right, I think I'm spinning it the right way. Am I spinning it the right way? Okay, great. You can see the thing. I have to do it backwards from what it actually looks like straight. So if I spin it this way, and on the bottom, I say what's the direction of velocity? It's the direction he'll go if I let him go. So if I let him go on the bottom, he flies to the right. Now, you notice you're like, that was a little bit, obviously I didn't do it perfectly. And there's an arc because gravity is affecting it. But we're pretending like gravity doesn't exist. Let's do maybe a more clear one. If I do it on the side, so if we look at the side here, either of the sides, let's pick the one that's maybe more interesting. So if I pick this spot, if I draw a little line, and then I make that line bigger, again, I'm getting my finger painting skills in today, it should go straight up. So, if I swing this correctly, yeah, good me. Oh gosh, it's always tricky. So if I release him at that spot, he should go straight up. And again, I'm probably not going to do it perfectly, but it gets the idea across. Yeah, there you go. Look at him. He went straight up. He did not make an arc because even though he was traveling in a circle, the second I let go of the string, why should he keep going in a circle? Nothing's holding him. The only reason he's going in a circle is I'm holding on to the string. The second I let go of the string, it doesn't know that it was going in a circle. It doesn't know it's passed. And so it'll just go straight up. And then obviously gravity pulls it back down, but there you go. Okay. So that kind of segues us into, so we talked about, going around a circle, we calculated the velocity, the tangential velocity. We also said it's 2 pi r over t, where t is the time for one revolution. We use capital T. That's called the period. We're going to see that later on at some point. We talked about radians. So today, what keeps it in the circle, and we've kind of touched on this, because the velocity vector is changing, it must be accelerating. The value of the velocity is staying, the speed is staying the same. It is going, whatever, let's just say it's 10 meters per second. It's going 10 meters per second at all points, but the vector is changing. Here on the side, sure, it's 10 meters per second. Let's just make up a number. But that's all in the y direction. So that's tangential velocity, but that's just in the y direction. If instead I'm up here, my y velocity is 0 up there. Again, I apologize for this horrendous handwriting. My pen's battery died. It takes quadruple A. If you didn't know those existed, I didn't either until I changed the battery. So the x velocity, that's the y. It doesn't even look like one. The y velocity here is now 0, meaning it went from 10 to 0. Now, where'd that velocity go? It's in the x direction. Let's make that look like a y. Oh, it's so terrible. All right, I'm going to do my best to not solve a bunch of mathy problems today. All right, so the x component is now negative 10. Negative 10. Whereas here, the x component, oh, it's awful. I hate this so much. But it's better than nothing. So, it may not look like the velocity changed, but when you break it into components, we can see the velocity vector did change. That's why acceleration means either my net velocity is changing, my speed is changing, I'm speeding up or slowing down, or I'm changing direction. Easy example of this, I can walk at a constant, whatever, let's just say 3 meters per second. I'm still walking 3 meters per second, I'm still walking 3 meters per second, and now I'm going backwards. Clearly, I was going to the right, my velocity was to the right, now it's negative to the left. I didn't change my speed, but I did change the direction. So, all of that is just to try to convey to you all, acceleration is not just the speed value changing, it's also the direction could be changing instead. So, we call this centripetal acceleration. Centripetal acceleration. Why centripetal? Centripetal means center seeking. It's towards the center. Centripetal is towards the center. That's where this, it sounds like center. Centripetal. The equation for this, I think I mentioned it to you all last class, but we didn't, it was in the last minute or two. It's VT squared over R. We're not going to spend the time proving this, deriving this. Feel free to look up videos of the derivation. It's just a bunch of geometry, which is interesting, but you don't really gain much conceptually. It's not from physics per se, it's a lot from just geometric kind of stuff. Feel free to check it out. But VT squared over R, take the velocity squared, divide it by the radius, and it's always towards the center. Always towards the center. And we're going to see today, when we get to forces, why that is. It'll be a little easier when we get to forces to explain why that is, and Demo Duck will come back in for that. But yeah, it's always towards the center. If you want to know the direction of acceleration at this spot, here in the top right, towards the center. You want to know the direction of acceleration on the bottom? Towards the center. Oh, over here? Towards the center. Real easy. Real easy to draw this one. Always towards the center, no matter where it's going in the circle. Anything going in a circle is accelerating towards the center. All right. So to make certain we're really good at this, a ball is being swung counterclockwise. What is the direction of the centripetal acceleration? At the point shown below, the point shown below is at the bottom. You have to remember which direction counterclockwise is. I believe in you. And while you all are doing this, I'll give you another joke. Oh, the answer is A is down, B is left, C is up, D is right. So things swinging counterclockwise. What is the direction of the acceleration at the spot located at the bottom? All right, my joke, which did not land very well with my high schoolers, but I thought it was funny. It's not oh no! Is it showing up to anyone? Oh, some people. All right. It is showing up for, I guess, 97 people. If it's not showing up for you, just come tell me at the end, and we'll shoot me an email or something. Woo! Great. It is working. Again, if it doesn't work for you, shoot me an email after class. So the joke is Gen Z should instead be renamed to the quarantines. Instead, Gen Z, we should instead call the quarantines, just because of COVID. Yeah, they're all great. Every joke is great. I'll do my best to remember to I tell my high schoolers one every day. I'll try my best to remember. All right, let's go for 5 more seconds. 5, 4, 3, 2, 1. All right. Through the beauty of the word centripetal, centripetal is towards the center. Ugh, with the pin that time. We did it. Woo! Counterclockwise was this way. Fun fact, it didn't matter that it was going counterclockwise. Centripetal is always towards the center. Clockwise, counterclockwise, who cares? So yes, oh, look at that. That's with my mouse. So that's the direction of my centripetal acceleration. My velocity, there we go, slow and steady. It's directly to the right. That picture wasn't very good. It should be directly to the right, but it's close enough. All right. Okay, so putting this in practice. An experimental jet rocket travels around Earth along its equator, just above its surface. There's the radius between, and this is kind of interesting. This is not the distance from it to the ground. This is the distance from it to the center of the Earth. Because this rocket is making, if you drew this circle, you would need all the way to, yeah, there it is. Who cares which way it's going? This is R. It's working. All right. At what speed must the jet travel if the magnitude of its acceleration is g? All right. So, what's given? Oh man, now we're typing this. Let's see what I can type to spare myself. All right. So step 1. What's given? We are given. Boop boop boop. Smaller font, doesn't want to. All right. We are given R equals 6.37 e to the 6 times 10 to the 6 meters. We are given, that's just G. So A equals G. If you really want, you can put the value of it. In fact, let's put the value of it. We know what G is. It's negative 9.8 meters per second squared. All right, so we know R, we know this. That's kind of all we got so far. What are we solving for? The speed, aka speed is just the magnitude of velocity. So speed, which equals the magnitude of velocity. Step 3, what equation? Just copy and paste this bad boy on over. Boom. All right, it's fairly straightforward from here, hopefully. We know A, we know R, we're solving for V. So if I rearrange this equation, we're going to find that VT equals the square root of A times R. And at this point, it's fairly straightforward. Just plug in the numbers, take the square root, call it a day. So V equals square root of negative 9.8. Now, this is one of those good situations where like, do I use the negative? Do I use the positive? We can immediately say if I put the negative in there, it's going to be square root of a negative, and that's not going to make any sense. So this is one of those where you just say, I'm going to make the acceleration positive here. Why? Because this thing's going around in a circle, and so we're not really dealing with ups and downs here. Especially because we're calculating speed, not necessarily velocity. So that's even why it said speed. If we did velocity, we would have to define a direction. So in that case, again, we're just going to say we don't need to worry about positives and negatives here. 37E6, you plug that in, and you get something. And at this point this is one of those, what is this a realistic answer? Is going to be a little tricky for us. Because obviously our answer here is going to be pretty large. So it equals 7,901.01 ms It's real fast, but it's a jet rocket, so that's fine. Jet rockets are allowed to go fast. Fun fact for you all, if you want to have another reference for how fast things are, 343 meters per second is the speed of sound. So in air. So in air, every second, sound travels 343 meters. So if you wanted to figure out how fast this is going, if you divided this by 343, this thing would be going Mach 23. That's real quick, but it's an experimental jet rocket. No humans are inside of it. The fastest, I think, plane, when I Googled this recently, we're learning about sound and stuff in high school, was I think like 7.2, Mach 7.2 or Mach 7.5, meaning on Earth, no one has gone faster than 7.5. Go into space and you can go as fast as you want, no problem. So if there's a human in this would be an unrealistic answer, but there's not a human in it, so it's okay. Anyhow, fast rocket. All right. Okay, so now we're getting into Newton's laws. So that's circular motion kind of done. Fairly simple, not too bad. 2 equations. Not too much fanciness I can do with those yet. Next week we'll do some fanciness with them. How do you cause an object to accelerate? All right. How do I make this duck speed up? Right now it's not moving. Now it is. I threw it. And what did my hand have to do? Push it. So what makes something accelerate? A force. Yep, so that's Newton's laws, he defined what forces are. And so that's what we're going to be talking about. It's a word that you've heard before. We're going to clarify some details about it because there's a lot of words that you've heard in everyday language, like force, like acceleration, like maybe velocity. But we have to be very clear with our definitions, and it will mean a slightly different thing than kind of the everyday use. A lot of it will line up, but we got to clarify some things. So, everything we've been doing so far has been kind of just the study of an object's motion. That's kinematics. Nothing here you never need to have like the definitions written down. But why? Why do things like when I toss it through the air, why does that happen? Why does it get pulled down to the earth? It's because of this thing called force that Isaac Newton came up with. Why do they accelerate? What makes something accelerate? When you hit your gas and the pedal in your car speeds up. Why does that happen? And that's where forces get involved. And so that's what we talk about today. This week is going to be kind of conceptual, and then next week we'll start applying the math to it. So we're just going to be talking about what are forces, Newton's 3 laws. So yeah, what is a force? Put very simply, it's a push or a pull. That's one way to define it. Very simple definition. It is a vector. Easy example of that. If I push the duck to the right, he moves to the right. If I push him to the left, he moves to the left. Clearly, direction matters. The direction you push something matters. Anytime we talk about vectors, that's really what it boils down to. Does direction matter? If so, yeah, it's a vector. So the force is a vector, and a physical contact is not required. Often we think of push or pull, and you think you have to touch something. But in all our free fall problems, they're all getting pulled down to the earth. In the air, they're not touching anything. Gravity. Nothing is touching it, and yet it is experiencing that force. So, most of the forces that you will think of involve something touching. But when you get to physics 2, you'll actually find that nothing touches. Anyhow, fun things to look forward to. All right, so there is 4 fundamental forces of the universe. 2 of them, one of them we'll talk about in this class. So gravitational force we will talk about in this class at some point. That'll be the first thing we talk about after test 1. The electromagnetic force is what you'll spend the entirety of physics 2 talking about. And these last 2, what I can explain to you is literally the extent of my knowledge. So the strong force. So you're going to learn in physics 2 that opposites attract and like charges repel. If they're being attracted or repelling, push-pull. So protons will repel, electrons repel, protons and electrons attract. But then kind of the next question is, okay, nucleuses of atoms are a bunch of protons together. If they repel each other, why are they held together? And it's not gravity. In fact, gravity is quite, out of all of these, out of the first three, gravity is the weakest. Out of the first three of these, gravity is the weakest, which is a really weird, because you're like, but it's holding me to this Earth. The Earth is massive. And again, later on in class, we're going to find that every single one of you is exerting gravity on every single person in this room. None of you know it, because it's really not that strong of a force. You need something massive to experience this force. But when we talk about electromagnetic forces, it doesn't take much for those to happen. Those are the reasons why you don't go through objects. Those are the reasons when you touch something, and you can, physics too, something to look forward to. All right, strong force, protons, what keeps them together? The strong force, I want to say a bunch of stuff, and it's going to sound made up, and this is the limit of my knowledge. What holds the strong force together? Well, what holds these protons together? Turns out they're made of quarks. Okay, so you thought protons and electrons are the smallest, they're not. Quarks are smaller than them, and maybe quarks are probably made of something else, and they're probably made of something else, who knows how far down it goes. All right, they're made of quarks, and these quarks exchange gluons. And that holds them together. Yeah, if that didn't tell you much, it doesn't tell me much either. That's the extent of my knowledge on the strong force. Literally what I told you, I think I heard from one teacher and one class, and that's the extent of my knowledge on it. That's probably the extent that you'll ever hear it mentioned again, unless you go into the depths of the internet and find things. All right, so that's that, right? You'll never hear it again, very likely, unless you seek it out yourself. Weak force is responsible for like uranium and plutonium radiating and breaking into smaller molecules. That's all I know about the weak force. No idea what. That's all I got. So anywho, the third and the fourth force exist. Why are they separate categories? Because they're independent from each other. As far as we currently understand, gravity and electromagnetic forces are completely separate of each other. They do not interact in any way that we currently know. Same with the strong force, same with the weak force. Something can experience all of these forces, but gravity can only, things with mass experience gravity. Things with charge experience that. The other things experience other things. But they're all separate from each other, so they have separate categories. There is this pursuit of the grand unifying theory that connects all of them together. Hasn't been found. Here you go. There they are. And we're moving on. You don't need to know any of this. Fun facts. All right. So yeah, there's different types of force. So that's one way to categorize them. What causes the forces? And then again, I'm not going to ask you all to define any of these, but it's just good to know kind of these terminologies. Contact forces are if you're physically touching. So conventionally what you expect. I push the desk. I'm touching it. I'm pushing it. Field forces are like the gravity that you experience. You do not have to be touching the earth to be pulled down by the earth. It's caused by a field. What's a field? It's a made-up thing to explain why it affects you when you're not touching it. Okay? Again, we'll see that in a bit. Fields are weird. You'll learn about them a lot in physics too. Great. Bunch of just definition-y, fun things. Don't need to know any of that for the quiz or test. All right. So getting to what we do know. There he is. Look at him. What a guy. Absolute lad. Genius. This guy did so many things. He came up with Newton's laws, which may not seem like a big deal, but he was the first person to kind of define some of these things. So obviously people back then knew if you pushed something, it moved. But they didn't develop the relationships between how does it move? How hard I push it affects that kind of stuff. So he defined all that. He also discovered universal gravity, the equation for that. He also discovered that white light is made up of all the colors. He came up with so many things. Really interesting fellow. Feel free to look him up, but that's what he looks like. What a guy. All right. Really good to give homage to him. So now we're going to get into, he has 3 laws we're going to talk about. 3 laws we're going to talk about, and they're very simple ideas. But the result of those ideas is going to be things you don't expect, things you're not used to. And we'll talk about why that is. Some of it will be very obvious, but the consequences of these expand upon your intuition. There's going to be some things that are not going to be intuitive to you. And we'll talk about why those are as we get to them. Some of them you're going to disagree with, and we just kind of have to process through them until we get to a place where all of these are true. They're called laws because this is based on observations. Everything I'm about to tell you all is not based upon an equation or based upon something else. It is literally foundational. If you observe reality, this is what you see. Whether you like it or not, this is how it goes. It doesn't say why, it just says it is. Laws just kind of say things are this way from observation. Theories use those laws they try to explain why that happens. Anyway, so if I fire a bullet in space, what will eventually happen to the bullet? Will it slow down and come to a stop? Will it get faster and faster? Or will it keep traveling until it hits something? So all physics is based on observations. And then we go from there. Using what we observe, we then build on that and try to understand why. But the only thing, and I guess you could even argue this, we are assuming reality is real. That is a fundamental assumption. That's one of the crazy things of physics, you know. Even physics requires faith, because you have to believe that reality is real and that your perception of reality is accurate. So that's kind of a crazy idea. But at the end of the day, there is kind of you have to believe that what you see is real and that it's not a fake simulation. It sounds silly, but if you think about it, that's fun philosophical things. All right, we'll go for 5 more seconds. We'll go to 55. So 5, 4, 3. Oh no! This is why it wasn't working. I apologize. If you have a physical clicker, you've probably been like, it's not working. Yeah, I didn't plug in the thing that registers physical clickers. I'll plug it in now. If you're one of those people, just come at the end of class and tell me and I'll give you the points. You'll shoot me an email or something. So my apologies. I only realized this now. I have no idea if it works at this point. I may need to close it and reopen it. All right. Apologies. All right. Let's see what we got. Great job, everyone. All right. I'm actually going to close this poll and reopen it. Again, if you're one of those people that had a physical clicker, just come at the end. Just shoot me an email. I'll give you the points. Easy peasy. I think for like the one. All right. Goodbye, class. All right. Because I think I have to do this for the thing to work. Okay. So, yes. The answer is it will keep traveling until it hits something. And the reason for this is described in Newton's first law. So the official definition is the one that if you Google it, and then underneath that you'll see my definition that isn't as accurate but helps me remember it. A body at rest remains at rest, or if it is in motion, remains in motion at a constant velocity unless acted on by a net external force. A lot of jargon there. Kind of hard to break down. In my own words, what do I describe that? Things keep doing what they're doing until acted on by net force. That's not zero. Until acted on by force. So, meaning, if you leave this room, you will expect this remote on this table to still be here next class, unless someone moved it. Someone acted on it by a force. Again, very straightforward. It's what you expect. Things that aren't moving stay not moving. But the thing that may not make, and the last problem kind of, y'all did great with that, something will also keep moving forever and ever and ever and ever until it's stopped. Now, again, the reason that may seem weird, again, y'all did great in the last one, in space there's no air. We're so used to friction and air resistance, and because that's what exists around us. We're not used to a reality without those things, because none of us have lived in space and all that kind of jazz. So, to that end, we're used to things slowing down. Why do they slow down? There's friction. There's air resistance. But if those did not exist, so like that bullet example, if you fired a bullet or a gun in space, it's one of the interesting things about hypothetical space combat. You know, if you shoot a giant gun in space and you miss, it's going to keep going. And if there's something in its way eventually, that's what's going to stop it. That bullet will travel. You shoot it at whatever crazy fast speed you fire that thing at, it's forever. So this has some interesting consequences in like low Earth orbit where we have, if a satellite breaks up into pieces, all those pieces are traveling still circling the Earth. And they're traveling very fast. To orbit the Earth, you got to be going real fast. Now, something else on the Earth, you can just imagine if something's orbiting the Earth like up and down and something's orbiting it left and right, those velocities are very different from each other. So even like a flake of, like a piece of paint, a little like piece of paint that chipped off something has the potential to cause extreme damage because it's going so fast. So they actually track every single object. Anytime like a satellite breaks up, every little fragment they actually are tracking. And you can look this up online, all the little fragments that are flying around. And they sometimes have to course correct satellites to avoid just like a screw that's flying through it because it's going so fast. If it hit that satellite would explode. And one of the consequences of this, I forget the name of it, you could get a cascading effect where if one screw hits a satellite and that satellite breaks, now you got a ton of pieces. Those are going to keep moving as well. Okay, what if those hit more? Then those are going to break. And then you get more. And there's kind of this fear eventually that if we put too many things into orbit, this gets more and more likely to happen. And if it happens, there could be so much junk flying around that anything else we put up will immediately get knocked out and we can never leave the planet again because there's a bunch of crap flying around at super high speeds. Yeah? Kessler syndrome. Oh, yeah, thank you, Kessler syndrome. So, but it stems from this, that they'll just keep flying around unless they fall back down to Earth. But why would they fall back down to Earth? They would, there is, like, the atmosphere extends forever and ever, so things slowly kind of get slowed down, but it takes some of these things a long time, the ones that are really far away from the Earth, but there's not many, almost like no air particles. So, fun facts. There you go. All right, there you go. So, if an object is slowing down, a force is acting on it. Your car, when you take off the gas, it slows down, not because you're hitting, like, obviously you can hit the brakes, but even if you're not, why is it slowing down? Because air resistance, because of friction. There is a force acting on it. If something is going at constant speed, the net force is zero. So, when you are hitting the gas on your car, there is a limit to how fast you can go. Because when you're hitting that gas, you are pushing your car forward. The faster you go, the more air resistance pushes back. At some point, those equal out. You are moving. When you put your car in cruise control, you're going 60 miles per hour or whatever it may be. You're still having to hit the gas. However much you're pushing your car forward is exactly canceled out by the air resistance when you put your car in cruise control. The second you take your foot off the gas, you'll start slowing down because that net force will no longer be zero. If there is no forces, there is no change in motion. Meaning it's not, whatever its velocity is, 0, 10, negative 10, a million, whatever that value is, if there's no net force, it stays that value. All right, so next question. Well, I'll leave this for a few seconds. So again, these are little fun little things that have all sorts of far-reaching consequences. And he was the guy to come up with this. It may sound really simple, but remember, Isaac Newton hadn't been to space. He had lived on the Earth just like we all had and was used to things slowing down, and yet he still came up with that idea that if something's slowing down, there's something acting on it. If it's not, it'll keep going forever and ever and ever. And he had no idea of what was going, they had the planets in space, and I guess you could look at those things. All right, what is harder to move on Earth? A small truck or a big truck? Should be very easy. We'll go to 30 seconds. Yeah. 40 seconds. I'll give that extra 10 seconds. What is easier to move on Earth?
What is harder?
Yeah. What is harder to move on Earth? Small truck, small car, big truck. Car, truck, same. All right. In 5, 4, 3, 2, 1. All right. Hopefully everyone knows. Try this is gonna match. Good job, everyone. All right. What's hard to move in space? A small rocket or a big rocket? Obviously, what has changed here? Pretend like we're really far away from the Earth, and there is no longer a gravitational pull. Yeah.
You mean move or maneuver?
It's a great question. Let's say get something moved from nothing to maneuver, or just what's harder to speed up? is maybe a better way to put this. What's harder to speed up, maneuver, change its velocity? What's harder to, let's go with speed up in space. That is a better way to ask that question. Because as we mentioned, once it gets going, it's going to keep going. Newton's first law, but here we're looking at speeding it up. All right, we'll go to a minute. In 5, 4, 3, 2, 1. The answer to this, it's the big rocket. Yeah, and this is where that intuition, and again, Isaac Newton discovered this stuff. The big rocket is still harder to speed up. And this is weird because you're like, but it doesn't weigh anything. And things that weigh a lot are harder to move. And that is true. But what Isaac Newton discovered, it has nothing to do with how much it weighs. It has nothing to do with the weight of it. Even though he had never been to space and never discovered, that things out, I may have known, he knew that gravity was zero out there. Even though he was never there to test that, what he discovered is that the force required to move something is proportional to its mass times however much you want to accelerate it. Or we could say the acceleration of an object, we could rearrange this equation. How much something will accelerate, how much its velocity will change. Take the force that you're acting on it. So A equals F net divided by the mass. Now mass is not weight. And that's going to be a weird thing for, mass. I know, we weigh things on Earth and we say kilograms. In this class, mass is not weight. That's a really important distinction. Mass here is not weight. Mass is how much stuff something is made of. How many particles? So, proton and electron have a certain mass to them. And so if we kind of add up all that mass of an object, all those particles and their contributions, that's the mass of an object. If I take demo duck here, let's see, before I say anything. No. All right. Okay, good. If I took demo duck to space, his mass would be the same. The mass of the duck on Earth is the same as the mass of the duck in space. The mass of you on Earth is the same as the mass of you in space. The weight of you on Earth is different than the weight. And that's a very important distinction that we have to make. Yeah?
Milligrams is the unit for mass.
So milligrams would be we would have to convert that to kilograms is the base unit. Milligrams is take kilograms and move it 6 decimal. Yeah, so 1 kilogram is 1 followed by 6 zeros.
Kilogram weight.
So this is where everyday use of kilograms is weight. But in a physics and an engineering context, kilograms is going to be mass. And mass is not weight. So, to spoiler alert, actually, you know what? We can just prove this. So, force is newtons. Mass is kilograms. Acceleration is meters per second squared. So this isn't really a spoiler. What is the acceleration we experience on Earth? Negative 9.8. It's g. So if you want weight, if you want the force due to gravity, that's all weight is the force due to gravity. The force due to gravity equals, I have to do this very slowly because I'm using a mouse and it's the worst thing ever, m times g. So in this class, we will not measure weight in kilograms. We will measure mass in kilograms. Weight is a force. And force in physics and engineering is measured in newtons. It's just one of those, they get used interchangeably here on Earth. It's not ideal, but that's just how it goes. Yeah. Then everyday use of kilograms is weight, but in a science context, kilograms is mass. And it's very important that you know that mass and weight are not the same thing. Yeah, again, that's one of those where I told you all some words we use in this class are going to match stuff you've used every day. Some of the words we use in this class have special meanings that are different than that. So, to that end, if we connect this to our last problem, if you tried pushing a giant rocket in space, somehow, you got out of your spaceship and somehow you had some leverage. I don't know how you'd have the leverage because obviously you can't push off anything in space, but let's pretend like you could. Maybe you were trying to push a giant spaceship away from another giant spaceship. You would have a very hard time doing it. It is very hard to move things with a lot of mass because we say they have a lot of inertia. Why? Because that's how the world works. Again, this is a law. This is an observation of reality. It's hard to move a lot of particles. That's just how the universe works. All of these laws, they're observations of reality. Isaac Newton discovered that the more material I had, the harder it was to accelerate. Not because of gravity. And an easy way to kind of give an example of that, if we put something like on a frictionless thing and we moved it left-right, I'm not fighting gravity if I push something left-right, assuming there's no friction. So if you try to push an object and there was no friction and it had a lot of mass, it'd be really hard to move. Even though you're not actually fighting gravity, you're not trying to lift it up or push it down, and you're not fighting friction. It's really hard to get rid of friction, but if you could do your best, you'd find it's very hard to move. So, again, one of those weird consequences, weird things that just shows how smart this guy was. And yeah, we're going to see that, and it applies regardless of gravity. All right, so using that equation, one of the things that we need to be able to do is kind of understand if I change a variable in an equation, how does that affect another variable? That's a skill that we're going to see throughout this class as we kind of introduce some of these relationships. Do we understand these equations express a relationship between variables? So if you change one of the variables, how does that affect a different one of the variables in the equation? So object A has half the mass of object B. If I want to accelerate object A 4 times as much as object B, how's the force going to compare? And there's a lot of things going on here. And the trick to this is that F equals ma. This equation gives me the relationship between mass, acceleration, and force. So as I change the mass, and as I change the acceleration, how does that affect the force required? We couldn't do these problems as much with kinematics because there was a lot going on. But as time goes on and as I kind of introduce equations like this that kind of relate variables together, through often just a multiplicative way. As the mass goes down, how does that compare to the force? So if the acceleration goes up, how does that compare? All right, we'll go to 140, so 10 more, we'll go to 145. I'm going to show you all how to do this mathematically and also how to make sense of it conceptually. 5, 4, 3, 2, 1. Okay, so the key to solving this is first we say, what's my original? So the force on object B is this. Just the original. It's got some mass. It's got some acceleration. If I look at the force on A, the force on A is the worst, equals, oh, I'm going to type this out. It's going to be so much easier. All right, through the power of typing. So, if I look at the force on A, that's going to be the mass of A times the acceleration due to A, which is like, okay, what? It's just good to label all these things. But the punchline's gonna be much easier. All right, great. So what? How does that relate? All right, so how does my mass of A compare to my mass of B? Well, the mass is half the mass. The acceleration is 4 times as much. Pull out all those constants. 4 times 1/2. So 4 times 1/2 times ma. I need twice the force. If I have half the mass and I want 4 times the acceleration, I just kind of plug in how those variables change, and it spits out the force needs to be twice as much as the original. So there you go. We'll play around with these more when my thing's working. I'll have an easier time. But yeah, how these work is you just plug in how the variables change and pull all the constants to the front. And that's the key here. If I half the mass, it's easier, but I need 4 times the acceleration, that's harder. So they kind of fight each other.